Thanks a lot. So I think you summarized it very well, what we covered so far yesterday. So I'll just continue today's session. Okay. So hey everyone. So today my plan is, so yesterday I just gave sort of an introduction about what reinforcement learning is. Okay. And like what is the current like struggles that people have with reinforcement learning, like the exploration exploitation dilemma, how to define the state space, how to define the action, what is the reward engineering, all those nitty-gritty details. Okay, so today I plan to dive into more of a toolkit exploration. So I'll today show you one toolkit that people use to write their codes for reinforcement learning. And in fact, you can write it too, because using this toolkit, it makes your life very simpler. So with just about 20 to 25 lines of code, you can start training your own reinforcement learning agent. Okay, so I'll be following this particular tutorial that was presented at a conference ICRA in 2022. So these guys have a nice schedule. So the first, I'll basically be covering this, getting started with gym and RLN practice, and the third one, which is hands-on session with gym and SB3. Okay, so I'll not do how the physics simulator works with robotics reinforcement learning. So we are only caring about the reinforcement learning aspect. We are not getting into the robotics aspect, right? So if I go here, let me minimize this. Yeah, by the way, you guys can see my screen, right?
Yeah, no worries. Also,
Okay.
one more thing. If anybody has any questions, you can put in the Q&A. There's no chat, but you can put it in the Q&A. Thank you.
Or you can simply unmute and ask. That is
Yeah.
also the best way, I would say. Yeah. Okay. So today we'll look at how one can use RL in practice. So there are two important toolkits or two important libraries that I'll be discussing. One library is called the GYM, and the other library is called Stable Baseline 3. Okay, just keep that in mind. We, at the end of today's session, you guys should be comfortable with what is a GYM and what is a Stable Baseline 3. Okay, we'll discuss this in detail. Okay, so some teasers, like how motions in RL looks like. Okay, so this is a robotics application. So you have a quadruped robot, and your aim is to make this robot learn how to walk. Okay, so all its limbs have a like unrestricted degree of freedom. So I mean, they have some restricted degrees of freedom. So they have two joints. So each leg has two joints, and there are 8 joints in total. So you want to make the robot figure out like how the motion of the joints should be, and these joints actually have the motors in them, right? So you basically have to ensure that the robot has a sensor. Through the sensor, the robot observes its surrounding or the observation. It takes the entire sensor input and then make sure that the equivalent action or equivalent thrust is passed on to the motors or the actuators, right? So it's like a direct sensor to actuator application that is happening over here. And of course, this is a simulation. So these guys have developed a simulator model for such kind of a robot, and then they can train multiple iterations to see how it works, right? So like this, for example, is making it learn how to jump. Okay. This is another example of how a robot can be made to jump using reinforcement learning, right? That again boils down to how you define your reward function to be. And based on the sensitivity of how your reward functions are defined, you can tune in the different traits, right? So here there are two different types of jumps you can see, and this is a matter of fact of how the reward has been defined. Okay. Again, some other application. Let's just. So this is another project that they will show as to how exploration can be done using RL. So if you see here, they are training directly on the hardware itself. They are not doing any simulation training. So they have a hardware setup and the training is happening directly on there. There is no transfer happening from software to hardware later on. So you see, the robot has to get into the green configuration. That is its aim. So it is trying something random and making sure it reaches the green state. Yeah, this is a four-legged robot that is learning how to walk. So this is a pure exploration phase, right? Yeah, here the input is only the image that it sees through the camera, and its job is to stay within the lane. Okay, so we saw 2, 3 different robotics example. Yeah, and you can see that certain tasks are easier and certain tasks are a bit more difficult. Like the walking example, it took them around 9 to 10 hours. Okay, but the car, self-driving car example, took them around 30 minutes. Any idea why that could be the case?
The number of control parameters in the walking case is like greater, I guess.
Yes, yes, that is true. The number of degrees of freedom in the walking case is very high. You can literally move your arms and limbs in any direction, right? So the configuration space is very, very large. Whereas in the case of a wheeled robot, the configuration case is strictly limited to what is the maximum angle a tile can turn, right?
Yeah.
So moving on. Okay, this is one example we'll look at. So this is something called as a cart pole example. Okay, just take a look at it.
Actually, I think so the audio is not shared. So
Oh,
the audio for the screen share is yeah.
okay, okay. Let me then skip this for now. Again, it's a racing robot that I'm just giving some examples before heading on to gym and stable baselines. I think we can skip this. Okay, so these are few examples that what deep RL can do. Okay, so today we are in the domain of deep RL. Okay, so whatever we covered yesterday was like a simplistic version of RL just to explain you. But the tutorial that we'll study is with respect to deep RL. But don't worry, you don't directly have to deal with any neural network. That all will be covered through the toolkit that we will be using. Okay, so this is reinforcement learning 101. So if you remember this diagram, so in RL, there are two components. One is the agent and one is the environment. Okay, the agent takes an action that gets reflected in the environment, and because of the action, the environment gets changed at next time step, and the environment returns a new observation or a new state to the agent. Okay, and at the same time, it also returns a reward to the agent to so that the agent is aware how good or how bad the action that it took was. Okay, so environment always has a mechanism to feedback a state and a reward. Okay, cool. Any questions on this?
No.
Also, anyone want to recap me what we mean by a policy? We discussed a word called policy yesterday. What do you think is a policy?
Policy is mapping of a state to action.
Yes, so it's basically a function, right? If I feed in the state policy, you can think of it as pi. Pi is a function. So pi of s is equal to a. It's a mapping of state to a corresponding action. And it's not a direct mapping, it's a probabilistic mapping, right? So you don't directly get, okay, this is the action you take. You get a probability distribution. So if you have 5 possible actions, you get, okay, action 1, you can choose a 20% probability, action 2 with 40, action 3 with 10, and so on. So it's a distribution that you get for the actions. And then it's up to the user which action you choose. So if you are exploiting, you choose the action which has the highest probability. If you are exploring, you probably choose some action which has a slightly lesser probability, right? So yeah, today's tutorial will focus on how a person can design the agent and how one can design the environment. Okay. So there are two components that a developer needs to design. One is the agent. So the agent design happens through a toolkit called Stable Baselines 3. An environment can actually be designed in multiple different ways. Okay, so you can either use a toolkit called Gym, you can use something called as EagerX. So EagerX is something that involves a slightly more gamified physics simulation. So you have all those real world simulations like the gravity component, the drag, the coefficient of friction, all these game physics information is present. We'll not go into much detail as to how EagerX works, but rather the example that we'll focus today will be simpler. Okay, not too complex. Okay, so this environment design is done through Gym, or you can choose also not to use Gym environment. You can, if you are interested, you can also handcraft your own environment. We'll see all that today. Okay, so outline, what is Gym? We'll look at what is Gym, RL on a custom task, and getting started with Stable Baselines 3. Okay, so far so good. You guys are still with me, right?
Yes, yes.
Yes, yes.
Okay. So yeah, what is Gym? A simple answer is Gym is basically an API. Okay. Gym is basically an interface or an API that is used as a decorator when you're designing an environment. Okay. This I'll make it more clear in the coming slides. Okay. So you guys are familiar with Python, right?
Yes.
Okay. And
Yes.
have you guys used TensorFlow, PyTorch before?
Yes, yes.
You're
Yes,
familiar
I've
with both,
used.
right? Familiar with both or one of them?
Not an expert, but I have an idea.
Okay. 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 That's fine. Yeah. Even if you are not familiar, it still should be fine for today's session. Okay. So a simpler way to know what is Gym is. So Gym is basically a Python library. Okay. So if you go to your terminal, you type pip install Gym, it will install the Gym library in your terminal in your base environment. Okay. The first thing you do is you create an environment. So when you say gym.make, you call an environment called cardpole v1. So okay, before that, I should show you what an OpenAI gym is. So this is basically a website called OpenAI gym. If you go here, so OpenAI gym is basically a website that is an API standard for reinforcement learning with a diverse collection of reference environments. So in this, they have lot of different environments already. Somebody has developed an environment and they have uploaded it over here. So if you are developing a new sort of RL algorithm and you want to test it, so there are multiple reference environments that one can take a look at, okay, to understand what is happening. So here, for example, it's a lunar lander example. So there is a lunar lander that has to land on the surface of the moon, and it has to make sure to land between these two flags, and the landing should be soft. Okay, and there are multiple examples. Like for example, there is a classical control environment. So these are all classical control based environment. Like this acrobot, you have to make it move in a uh, circular motion. Cart pole is the case where you have a car and you are balancing a stick on it. Okay, mountain car is you have certain thrust and you want to reach top of the mountain, right? There are multiple classical control based algorithm, sorry, environments. Like if you click on each of them in, let's say, cart pool, so you know what the action looks like, what the observation looks like, how one can import. So here they have done generation.make cart pool v1. That is something also we were doing. We were doing gym.make cart pool v1. So it's like dot make is a way to import an existing environment that is present in the OpenAI Gym repository. And there are hundreds and thousands of environments present in their repository. Okay. You just need to know the name on what to call. So here the ID is cartpole/v1, right? Similarly, you have a mountain car example. You have a pendulum. Okay. And you also have a description as to how they work. What is the task? What do you have to do? If you go through the website, you know all the information about what they have done, right? And these are like classical control environments. You also have box 2D, like a 2D box kind of an environment where you have bipedal walker. Okay, then you have a car racing. You have this lunar lander. Okay, these are all some examples of the box 2D. You have toy text, making an agent play blackjack. This is the cliff walking example. If you remember, we saw like there is fire over here and there are wind over here. So you should try to reach here by taking a longer path. So this is a pretty famous example called cliff walking. Then there is a taxi world example. So passengers pop up at any of the 4 points and they choose any drop off location at any different position. So a taxi's job is to pick up a passenger and drop to their designated location. Then you have this frozen lake example. So you should not fall into the puddle and try to reach the goal. Okay, so these are like toy examples. On top of that, you also have Mujoko based environments. So these are like physics. They are making use of a physics engine called Mujoko Pi. So these are slightly more complicated, where they have different environments. If you remember, we saw the four-legged robot walking on similar environment. So that was also Mujoko setup, right? And these are slightly more complicated because it's like if you have a real world robot with you, So you first create a simulated URDF model. You upload it to such kind of an environment, so you can train it multiple times without any damage to your actual robot, right? But then the challenge again comes as to once the software learns the learned behavior. Now, if you want to transfer it to the real robot, now does it still hold? Because that's also a key issue, right? You don't always see that working in real life. Whatever works in simulation doesn't always necessarily transfer to a hardware robot. So there is a big gap in that where people are studying a lot these days. So it's also a very interesting research field if you want to explore the sim to real aspect. Okay. And yeah, so there are multiple Mujoko environments. You have Atari based environments. Okay, so these are Atari based games that this is like one of the earliest example of the success of reinforcement learning, right? So back when deep reinforcement learning was not very popular, they showed that these kind of Atari games, a machine can actually beat a human. Out of 50 or 55 Atari games, the RL machine could beat the human expert in 40 to 45 of these games. Okay, so this was a big achievement back in those days, like early 2015. Okay, so this is all the famous Atari examples you can see. You can simply train your RL agent to learn these things, right? So go through this. You also have third-party environments. You have Flappy Bird. You have dynamic algorithm configuration. There are actually a lot of environments. If you scroll through it, even only this website only lists a select few. I'm pretty sure there are hundreds and hundreds of environments that are already existing. And the best part is, let's say you create your own environment, you can also upload it to this particular repository, right? So there is also a method to do that. So let's say you create your own, you come up with your own game, you design your own environment. You can also upload it. And once you upload it, you will attach a label to it. And users all over the world can directly use your environment for their purpose. Okay, that is also a possibility. So here, what we are doing is when we say gym.make, we are calling cartpool v1. So we saw the cartpool v1 example, right? Let's see that again. What the cartpool v1 is. So it was a classic control, and we have the cartpool. So the goal is there is an X plane where there is a cart, which is, or there is a trolley which can only move in this direction, and there is a stick which has to balance. Okay, so the aim is that the stick should not fall down. Okay, so it has to continuously keep moving so that the stick is kept uptight, right? Okay, so first line is create the environment. You created the environment. Second is reset and get first observation. So what does a reset function do? Any idea? Yesterday we saw this reset, right? When I showed the multi-arm bandit. What's the purpose of a reset?
Initiate it to 0, like
Yes, any starting state. Initialize it to 0 or any starting state. So here, for example, the reset is the cart is at the center of the screen and the pole is standing at 90 degree. Okay, that's the initial configuration. And then you start, right? Or it could be anything depending on the environment that you're using. So dot reset is actually a function of gym. Okay, because your environment is a call to a class variable called gym.make cartpool v1. So this env is basically an object. So this object has multiple methods. One important method is reset. When you do reset, you get the first observation. So you store it in observation. Now step in the environment with random actions and display the environment. Okay, so what you're doing is for dash in range 100. Basically, I'm running a for loop for 100 time steps, right? So this env.render mode. So if you call the render, it brings you the screen that we have, the rendering screen. Okay, so it shows you the simulation that is happening in real time. So if you don't do that, then you can still see what is happening. I mean, you won't see what is happening, but you will. You can still know what actions it has taken and what observation they have. Rendering is just to show it on screen what is happening, right? And then action is you do env dot action space dot sample. So what it is doing is I'm choosing a random action. Okay. I'm choosing any random action. I do that by env.actionspace.sample. Again, these are all predefined in the gym environment. Okay. We'll look in detail on how to create your own gym environment tomorrow in tomorrow's session. Okay. But today we'll just take a look at pre-existing gym environments. So one is actionspace.sample. So you choose a random action. And then here, the step function actually takes the action. Okay. So env.step, you feed in the action. So it's like that particular arrow, right? The agent gives the action. Now step function basically is where the environment takes in the action and gives you the new observation, right? So you get observation, you get the reward, you get done, and you get info. Okay. Observation is the new state that you get. Reward is simply the reward that the environment returns back. Done is basically a Boolean variable. Okay. So it's either true or false. Done is true when the goal condition has been reached. Okay. Or the episode has been a success. So once done is true, you should close the episode and you should restart everything again. And info is basically an empty dictionary. So if you want to return any additional information, that can be passed through this info variable. Okay. So env.step returns these four values to us. And then, yeah, end of the episode is if done. So if done is true, then you reset the environment and then you restart. Okay. Okay,
What's
clear?
the
Tell.
human mode over here in
Sorry?
env.run? What's the human mode? Mode equal to human.
Yeah, so there are different modes. You that is also specific to what environment that you're using. So here, for example, human mode is simply this kind of a mode that you're seeing over here. So this is like a more high resolution image. So if you do a 2D mode, then you can probably see a pixelated version of this thing. So based on different modes, you can see different resolution of the rendering that you have, right?
Okay.
Sometimes if you want these only to be in the form of images, so you have another mode set up for that. I don't know exactly what that mode is, but you can see, instead of seeing it as a video in itself, you can actually save images for each step.
It is RGB
So
array, if I'm not wrong.
yes, RGB
Mode
array
is
is the
RGB. Yeah.
yes. RGB array is the mode for saving images, right? Okay, so the crux is here we are taking random action. We don't want to take this random action, right? My RL here should give me what action I should take, right? This line number 14 here should be the place where my RL agent steps in and decides for me what action I should take. And this is the whole setup. Okay. So if you see, it's like about 21 lines of code where you have kind of defined how your environment should be. You're making a call to the environment. You can simulate an episode of your desired environment, right? Again, this is assuming that you have an environment that is in a ready format for you. Here we have a carpool V1 environment. But let's say if you're doing research, if you want to, let's say for the traffic control example, you might need to create your own environment with your own set of rules, right? That we'll look at in detail in tomorrow's class, how one can create their own environment with setting up their own rules. Okay. Today we are just taking a look at this existing library, right? All good. Any questions so far?
No, it's clear.
It's clear, right? Okay. Okay. Live demo. I think I already showed what the gym is. Gym is basically a collection of environments. You have multiple problems or multiple like very standard examples that people use for advancing the research in RL. And this basically makes life simpler for them. So you just have to call you just do a gym.make, call the respective environment and directly start training or testing. Even you can use it to benchmark if you develop a new algorithm tomorrow, you can use it to benchmark against these kind of environments. And this is a standard actually in the RL community. Most researchers all over the world follow this standard of OpenAI Gym and try to make their environment as much compatible with the OpenAI Gym framework as possible. Okay, so we'll look at what the compatibility is tomorrow. Okay, so there are multiple practice tips and tricks. So one can maybe visit this website to know what those tips and tricks are. But today we will talk about how to define a custom task. Okay. So defining a custom task, right? So what comes in the definition of a custom task? One is the observation space. Okay. So can anyone tell me what we mean by an observation space?
Space where the object will work.
The space where the what?
Object will have to the environment.
No. Observation space basically is the set of all possible observations that an agent can see. Okay. It's a set consisting of all different possible observations that an agent can see. Okay. So it can be either a continuous space, it can be a discrete space. Right? For example, if you take the the tic-tac-toe example. So there you have each box can be filled either with an X or a 0. There are 9 boxes. Okay. So the total possible observation is 2 to the power 9. Agreed? And that is a discrete kind of an observation. Okay. So you can only observe 2 to the power 9 different observations. But if you go to something more complex, like a self-driving car, where you are seeing the image in front of you, so it's a continuous world, right? So there also you need to define what the observation is. So that if you are in a continuous space, you need to define what is the range of pixels, what is the range of value each pixel can take in the image and so on, right? Clear?
Yes.
Okay. Yeah, please stop me if you don't understand anything. Okay. I'll be happy to answer. Okay. One question to you guys. So you see, I have used these two terms, state and observation, interchangeably, but actually they are not the same. There is actually a big difference between what a state is and what an observation is. What do you think could be the difference? When I say the environment returns a state to the agent, that is not always true. Sometimes the environment returns an observation to the agent and not the state directly. Both have a different meaning.
There are some partially observable environments where the actual state of the environment may not be necessarily the one which is observed by the agent. Basically, the agent doesn't know the complete environment. So that is why observation and state can be different.
Yes, that is correct. Observation is basically some partial knowledge. State is like the complete knowledge. Observation is what the agent observes, has a partial information, and through that it infers what the full state is. Okay. One example would be, let's say you go to a doctor, okay, to get yourself diagnosed with what could be happening inside you. So what the doctor does is the doctor performs a set of tests. Okay, he takes a look at your symptoms and he asks you a set of questions. How are you feeling? Good, bad? And based on your responses and the test responses, he makes an inference. Okay, this could be the possible disease that the patient is suffering from. So the actual disease is the state. Observation is what the doctor has access to, the information. Okay, and based on the observation, the doctor makes a prediction on what the state could be. Okay, this is clear, right?
Yes.
Okay, so in most cases, let's say in a robotics application case, most of the time robots don't have access to the state, or in most cases they don't know what a true state looks like. Okay, state is the full information, like what are the important things that I need to take from this kind of a observation that I have. For example, if you're creating a self-driving car, right? So all you have in front of you is an image. Okay. Now the whole image is the observation. In the image, you have to make a depth estimation. Like through the image, you want to understand if there is a tree in front of you, how far that tree is that constitutes the state. You need to make a inference on how far the nearest car is, how close you are to a lane. So the observation is what you get, and what you extract out of it are the relevant features that constitutes your state, right? So you need to extract those features out first. Okay, through this image, I can understand that the tree is, let's say, 50 meters away. The lane, I'm on the correct lane, and so on. All these things are state and observation. So yeah, here OpenAI Gym calls it as observation, and we'll also follow the same notation. We have an action, and the environment returns an observation. Okay, both are different. Ideally, environment should be returning a state, but 95% of the time, the environment doesn't return a state. It returns an observation. The agent has to make an inference as to what all relevant state variables it can extract out of the observation. Okay. Second is action space. Action space is the set of all possible actions that you can take, right? So for the multi-arm bandit case, let's have n different slot machines. What do you think would be the action space? I have n slot machines. What is the action space?
N.
Yes, correct. So I have n different options, and I can only pull one of the option at any given time. So there are n possible actions. Now let's say I'm come back to the self-driving car example. Let's say I am controlling the steering of the car. So what do you think would be the action space like? So let's say the wheels can steer from, sorry?
It will be 2, right? The action space.
No. You
for
don't,
this
you have,
right, left, right.
no, steering also you control it, how much you want to steer. It's a continuous example actually. So let's say your car can steer plus 50 to minus 50 degree. Okay. So the action space is all the different angles that exist between plus 50 to minus 50. Okay. And you can actually choose to steer either 1 degree, 5 degree, 50 degree, depending on the observation that you have in front of you. Correct?
Yes.
Okay. So an action space can be continuous, can be discrete. Observation space can be continuous, can be discrete. Okay. Third is you want to define a reward function that we discussed, right? There is an inherent assumption that reinforcement learning makes. The agent is only as good as the reward function that we define. Okay. So defining a strong, robust reward function is necessary to define a custom task. Okay. You have to define what the space of the observation is, space of the action is, the reward function, and lastly, the termination conditions. Termination conditions is the goal conditions, like where do you think the episode should end, right? So these are like the four. What do I say? Components that are used to define a custom task, right? Now, okay, come back to this RL101 example. Now it's RL102, this image. Okay. So the environment consists of the observation space, the action space, the reward function, the termination condition. So what the environment returns is in blue. So the environment returns the observation, the action from the space. Okay, one of them. So when I did that action space.sample, what I was doing is, so I have all possible set of actions. I'm randomly selecting one action out of that space. Okay. In the example that we did for the cart pole one, right? And at the same time, the environment returns the reward function and the termination condition. So the environment also tells the agent, okay, the termination condition, whether it has been met or not. So we had the done variable, right? Done is true or false. So done is true if certain conditions are met. It is false if certain conditions are not met. Okay. And the agent controls what the algorithm is, what are the hyperparameters that the algorithm uses. So this is from the agent's control parameter. The environment decides what these 4 parameters should be. Okay. Now, choosing the observation space, right? So the observation space should have enough information to solve the task. If you give if your space that you're defining is not adequate, is missing out certain information, then the learning would be affected by that. Okay, so the observation space should be chosen such that enough information is available to solve the task. It do not break the Markov assumption. Okay, so there is a new word today, like Markov assumption. Any idea what this could mean? Are you guys aware of the Markov property?
The future is independent of the past given the present. Like that was
Yes,
a statement.
yes, you're correct. So it's like the current state that you are at right now contains all the information that how you reach there, or what are the different ways you reach there. As in, the current information is complete in itself. You don't have to go back to, let's say, 2 time steps before, 3 time steps before to understand how you reach there. The information that you have at time t-1 is enough to make a prediction on what should I be doing at time t. Okay, so that is the assumption, and you should make sure that the observation space does not break this Markov assumption. That is, the observation that you have in front of you should be complete in itself. Okay, you should not be referring to any past observation as to how you reach that particular observation or so on. The current observation that you have is complete in itself. And third is normalize. What do we mean by normalize? Any idea?
Get the values to a particular scale.
Yes, you want to scale up the values to a particular. Yeah, do you want to basically bring everything between the 0, 1 or the -1 to 1 scale, right? Reason being, let's say, again, come back to the self-driving car example. So let's say you're controlling the steering, you're controlling the acceleration, you're controlling the braking parameter, you're controlling the transmission. Okay, each different component will have a different range of observations. Okay, at the action space, I don't know, let's take an observation look. Let's say observation is you are observing the distance to the nearest obstacle, the distance to the lane, or the distance to the nearby vehicle. And all these distances have a varying magnitude, right? So the distance to a tree might be far away. The distance to the neighbor car would be lesser. Okay. So you want to bring all of them to the same footage. So that's why it's very important to normalize everything between 0 and 1, right? So we come to the cart pole example. We know what the cart pole example is. There is a cart that is moving in the x plane, and there is a pole that is being balanced in the y plane, xy plane. Your aim is to keep the cart pole straight and not let it fall down. Okay. So what does the cart pole observation looks like? Okay. Again, this is something that you can find in the. If you go here, you can see what the observation looks like. But we'll look at here simply. So the observation is basically type 4. Okay, box 4. I'll define what a box variable is. Okay, just hold on. So there are 4 observations that is enumerated over here. So first one is the cart position. Okay, along the x-axis. Minimum it can be -4.8. Maximum it can be 4.8. Actually, the x-axis is between -5 to 5, but here they are cutting it from -4.8 to +4.8 because they don't want anything to go outside of the screen, right? Because the cart pole has, from the wheel, they are taking the position. So here they have defined it to be between -4.8 and 4.8. So at any point of time, my cart cannot go outside these 2 bounds. Okay, this is a hard restriction that we have. If it goes outside, then we don't know what to do. Okay. Again, one can set this observation to the choice that you have, but again, that's the choice of the developer, the one who is designing the environment. Okay. Then this is the cart velocity. Like, what is the velocity of the cart? And the range is from -infinity to +infinity. The pole angle. Pole angle is from -24 degree to +24 degree. Okay. So the pole, if it is standing up straight, it's 0 degree. And from the y-axis, it can go -24 degree to +24 degree. If it goes beyond that, we assume it's a failure case, because beyond 24 degree, it will fall down. That's what these guys have defined. So the pole angle should be maintained between these two values. If it goes outside, then there is no possible action. It's a failure case for us. Okay. And the pole's angular velocity is again from -infinity to +infinity. Okay. So these are 4 observations. And if you realize, all of these observations are continuous, right? So cart position takes a continuous value. The velocity takes a continuous value. This takes a continuous value, and this takes a continuous value. So you think of it like a 4D space. Okay. Your entire observation is a 4-dimensional space where each dimension is denoted by these different components. Okay. So try to imagine something like that. And all of them have a continuous quantity. Okay. So this box basically is a variable that tells me that whatever observation that I have will be continuous in nature. So box basically denotes continuous. So when I say box 4, type is box 4, that means I'll have 4 variables and all of the variables would be continuous. Okay. And here we are defining the observation low and high. Okay. So the observation high, this is a commented part, right? So this is actually the code part. So you define high is equal to, so x threshold into 2. So x threshold is 4.8. You multiply it into 2. So you have the whole space. You have np.info float 32.max to define the +infinity, -infinity. Then you have the theta value you are defining, and then you define the theta dot value, right? And the d type is float np.float 32. And that's how you define the entire observation space. So you write self.observation space is gym.spaces.box, box y, because all the observations are continuous in nature. Okay, your low is simply the negative of the high, because you see, this is the high values, and the low is simply the negative of that. So that's what they did. So low is negative of high, to put a minus sign in front of the high, and high is high, and the d type is this. So these 3 parameters are necessary to define the observation space. So once you do that, you're done. You defined what an observation space looks like. Okay. All good till now?
Can you explain why it was X threshold times 2?
So it depends what this X threshold is that they have taken. We don't really know, right, what their X threshold is.
Okay. Okay.
Yeah. Yeah. Okay. And this is the whole setup of the observation space.
Initially, we are doing trial and error with the values, right?
You are not doing. You are doing a trial and error, but you are trying to basically make sure all the observation should lie inside the space. Yeah, in a way you can say, but most of the time you always take a very high, a bigger assumption, right?
Yes. Yes.
But there is also a problem with that. If you take a very big enough observation space, then the exploration would be much larger. Okay, that is also a trade-off. You don't want to explore a lot. If you have a smaller observation space, then your exploration would be in a smaller region. Compared to if you make it infinitely large, then the exploration would be very large. Okay.
Yes. Yes.
Okay. Now choosing the action space. Again, action space can be discrete or continuous. Okay. You are basically taking a look at what the complexity of the action space is and what the final performance is. So the action space looks like this. So here it's a type discrete. We saw type box, right? Box means it's continuous. Discrete means you have just 2 different actions. So there are two possible actions. One is 0 and one is 1. So you have action 0, which is push cart to the left, and action 1, which is push cart to the right. Okay. You have just two actions. So you think of it like you're playing a game. You have the left key press and the right key press. So left key press moves it by some amount. Right key press moves it by some other amount. Right?
Yes.
Okay. So to define the action space, you have gem.spaces.discrete2. So what you're doing is you're defining the action space to be any value between 0 and 1. Right? So if it was a continuous action, I would have had to describe it using box and then define what the low is, what the high is, and so on. Okay. So this is the action space, correct? All good?
Yes.
Okay. Now coming to the reward function.
So is the input over there automatically assigned, or do we have to choose it later on? The 0 and 1s.
Automatically assigned, doesn't?
Right now, we pass 2 as a parameter, right? So in the comments it's showing 0 and 1. So let's say if it was 3, so what would the input look like? What would the number
It could be 0, 1, 2.
Okay, so it will always be a numerical value.
Yes.
Okay.
Everything is a numerical value. Action, observation, everything is a numerical value.
Yep.
Okay. So here 0 denotes left and 1 denotes right, but it can also be the other way around. It is depending on how you define it in the environment. So if I choose 0, action as 0, the environment should know what 0 is and take the step accordingly. And if I press 1, the environment should know what 1 is and take action accordingly. Okay. This information, what is 0, what is 1, should be present with the environment. Okay. Now choosing the reward function. So start with reward shaping. So reward shaping is an important parameter. What we mean by reward shaping is, so let's say there are 3 components of reward. Okay. Let's say again, self-driving car, you need to know what reward is, right? So you give reward for different components. Like for staying in the lane, you give certain reward. For not crashing into an obstacle, you give a certain reward. For following a traffic rule, you give a certain reward. So there are 3 or 4 different reward components. So you call it as reward 1, reward 2, reward 3, reward 4. And eventually your final reward is a linear combination of all these rewards, right? Clear, right? What we mean by reward shaping.
Can you show an example for
example? Okay, let me check reward. Trying to find an example to explain. Just hold on. Okay, let's take a look at this. So what these guys are saying, you might not be able to hear the audio. So what they're saying is there are different mini components of the reward, right? So for example, the cart pole example. Here the reward is for each time step, the pole is between -24 to +24. You give it a reward of +1. So there is only single reward component, right? But let's say you are looking at the lunar landing example. which was over here, right? The lunar lander. So there are 2-3 components of the reward. One is you should stay within this 2 flags, and the second is you should make a soft landing. So there are 2 components. Okay, one is the reward one, where is you want to make a soft landing. Second is you want to stay within these 2 flags. So you have reward 1, you have reward 2, but eventually your reward should be a single parameter, right? You are passing reward as a single value. So the simplest way to do is you take reward 1, you take reward 2, you sum it up together and pass it as the overall reward. Now the issue with summation is you don't know what is the weightage you want to give. Okay, let's say I care more about making a soft landing than making it land between these 2 flags. So my first priority is the soft landing. So maybe I'll do something like 0.75 times reward 1 plus 0.25 times reward 2. That is what shaping is. Like you're tuning the different weight components so that you achieve your desired goal.
Yeah,
Is that
I got it.
okay? Okay. So yeah, reward shaping is important. So that is simply referring to how you can tune your different reward functions. Like I said, there are primary and secondary rewards. You have a primary goal to achieve, and there are some secondary components. Shaping is what is the weightage you want to give to each component. Third is again normalize. Always normalize your reward function, right? Because you want everything to be at the same foot. For the cart pole problem, reward is very simple. If not done, reward is 1. So every time done is not true, you do a reward 1. So when is done true? Done is true when the pole falls down, or let's say you reach 100 seconds. Okay, so if for 100 seconds the pole didn't fall down, then the done is true. Or if the pole goes below -24 or +24, then done is true. So each time done is not true, you give a reward of 1, and that reward gets added up. Okay, so eventually, so for each action you get a reward, right? So at the end of the episode, you have multiple state action pairs. So for each state action pair, you have multiple rewards. So you have 1, 1, 1, 1, 1 for each time it didn't fall. And then in the end, you sum it all up together. So that will give you the total episodic reward. This is the instantaneous reward. Okay. Clear?
Yes.
Okay. Now termination conditions. You can either do an early stopping, or you can give a special treatment needed for timeout. So let's say your episode is running for infinitely long time. You want to make sure it stops after a certain time. Let's say your cart pole agent learned how to balance the balance the pole, and it is going on for a long time. You would actually want it to stop after a certain high number of steps, right? So this is either early stopping. Early stopping is when it was a failure case, and special treatment needed for timeouts when we are too successful. You want to cut it down in between. And termination conditions should not change the task. Okay, that you are not actually hacking into the reward function. Termination condition should be separate from the reward. Okay. Now for the cart pole, the termination is very simple. If x is less than or greater than the self.x threshold, then it's a false. Or if the theta is less than or greater than the self-dot threshold radians, right? So you see there is a bool variable and there is a or condition. If any of this condition is violated, so this becomes true. Any of this condition becomes true. So because you're using an or function, the whole thing becomes true. So your done is true if any of these 4 conditions are violated, right? So x should not be less than minus x threshold, not be greater than plus x threshold. Theta should not be lesser than the minus theta threshold and not be greater than the plus theta threshold, right? And this is how you register a gym environment. So there is a function called register. So you create an ID. So the ID is cartpole v1. So if somebody wants to use it, they'll do gym.make cartpole v1. And then you have the entry point, you have max episode steps. So here the max episode steps is for 500. Okay. So the episode runs for a total of 500 time steps. The reward threshold is 475. So all these different parameters you do. And once you execute this code, then your environment that you have created will get registered in the OpenAI Gym repository. Okay. Okay. Any questions so far?
So in this particular environment, we don't have like a goal state, or is it just
Yeah.
like try not to get terminated, basically?
Yes. Yes. It's like a continuous world. Like for example, you remember this game called Temple Run. It doesn't have a goal, right? You just have to stay on the screen for as long as possible. Or for example, Flappy Bird. You want to stay on the screen as much as possible. So each time of survival is a reward for you. So this is similar kind of a setup. So you don't have a goal, but you do have a termination condition.
Yes. Sure.
Okay. Yeah. So what's next? So Gym is basically an API that is used to decorate your functions. So once you Gym is basically used to define what your observation space should be, action space, reward, termination conditions should be. This is the environmental aspect. Then there is something called eagerx that they look at. We won't go into detail what eagerx is. What's next? What's next is stable baselines 3. Okay. Stable baselines 3 is more from the agent's perspective. So the agent controls what algorithm you are using and what hyperparameters you are using. Okay. So hyperparameter optimization is done through a library called Optuna. We won't cover what Optuna does for us. We are only looking at stable baselines 3, how one can implement their RL algorithms. Okay. So Gym API is used in the design of the environment. This we are clear. Now we want to actually train the agent, right? So if you remember, we did that action is equal to env.action space dot sample, where we were taking a random action. Now we don't want to take a random action anymore. We want to take an informed action. Okay. So stable baselines 3, what is it? It's a library. Okay. Stable baselines 3 is a library that is developed with PyTorch as a backdrop. Okay. So you have stable baselines, simple stable baselines 2. Those are developed for TensorFlow. Stable baselines 3 specifically is designed for PyTorch. Okay. So based on your preference, one can choose. I usually go with stable baselines 3 because it's simpler, and this is something that I'll cover today. Reliable implementation of RL algorithms. It's user friendly. You focus on model-free single RL agent. Okay. So it only supports single RL agent. You don't multi-agent RL is not supported on stable baselines 3. Okay. And then it favors readability and simplicity over modularity. Okay. Some features. So these are the different RL algorithms that it is using. Okay. So these are some of the state-of-the-art reinforcement learning techniques that people use. Okay. So these are all deep reinforcement learning algorithms. So don't get too worried on seeing these notations. So this probably will be clearer to you once you take your RL course or once you do some additional reading. So you actually understand what is happening inside the RL algorithm, how the optimization is happening, how the backpropagation is happening. But stable baselines 3 assumes that all these algorithms are already there. You don't have to touch these algorithms at all. You just select an algorithm and implement it. Okay. So these are the supported algorithms. It has a clean and simple interface. It is fully documented. You can Google about it and it will come up. So, okay, one important site I should tell you about, something called Spinning Up AI. Okay. So there is a website called Spinning Up AI. So there actually you have all information about what reinforcement learning is, the key concepts in RL, what can RL do. You have policy optimization. So it's I think a good website that you should look up today. Okay, so there are different algorithms. Okay, that they know that they have used. So there is something called vanilla policy gradient. There is proximal policy optimization. These are actually the algorithms, like PPO is proximal policy optimization. So if you are interested, of course, this is a very big jump that you're making, because first you need to understand what RL is. You need to understand what a classical RL is before jumping into this. But yeah, if you are directly doing an implementation, because nowadays most people are using deep RL. Okay, so if you are interested, you can bookmark this website and keep visiting it if you have any doubts with regards to the algorithm implementation that you have with you currently. Okay, but stable baseline 3 kind of abstracts that out for you. You don't really have to worry about those things. Even if you don't know what each of these algorithm means, you can still go ahead with your implementation, right? And it is comprehensive. Like you have all this tensor board logging, you have different callbacks. All these features are also available with stable baselines 3. And it also has a training framework included, something called as RLZoo. We'll discuss what that thing is. And you have a beta version of it called SB3 contrib, which has some other RL algorithms like QRTQN, TQC, TRPO, recurrent PPO. So there is a beta version of it that is used to implement like secondary algorithms that you that are not present in the original SP3 implementation, right? So getting started. Okay. So what you do is you import gem, you import from stable baseline 3, import SAC. SAC is an RL algorithm. Okay. So from stable baseline 3, I imported this particular RL algorithm. Train an agent using soft actor critic on pendulum V1. So this algorithm is called soft actor critic. The environment is called pendulum V1. What is the pendulum V1 doing for us? Let's see. Somewhere here, right? They had pendulum. Yeah, this is the pendulum environment. So the thing is, there is a pendulum which is attached to a single screw, and you are basically trying to move it such that it stays up. Okay, so you are first making it move left, right, swinging it. Eventually, you want to make it stand 90 degree in an upward position. That is the pendulum example. Similar to the cart pole example, but just that you start with your pole facing downwards instead of upwards. And the degree of freedom is just 1. Okay, you can only move in a circular direction. Okay. So you do gym.make pendulum V1. You create a model. Okay. So model is basically the policy that you want. Okay. So you say SAC MLP policy, define the environment, and you do verbose is 1. Okay. So these are like small decorators. When you do verbose is 1, you can actually see what is happening, all the logging and all those things. Even if you don't, it is still fine. But yeah, try to use what they have used so far. So like I said, this is an MLP policy. What is an MLP again? We discussed something about MLP yesterday, right? And we discussed what a deep learning is. We had briefly touched upon it, but yeah, if somebody remembers, please let me know.
Multi-layer perceptron.
Okay, what is that? It's a simple neural network, basically, right? So you have a neural network, you have the input layer, you have a bunch of hidden layers, you have an output layer. So if you want to implement a simple neural network, you call the MLP policy. Let's say if you want to implement a CNN, a convolutional neural network for your RL training, wherein you directly take the image as input, right? So if you have image as your observation, you need to first extract features from those images. So there is a CNN policy. If you want to use an LSTM, so you have an LSTM policy. There are different bunch of policies, but for our purpose, mostly MLP policy works if you have a simple enough input space. Okay. Now, You have defined the environment, you have defined the model. Now you simply train the model. What you're doing is model.learn total time steps 20,000. Okay, this is where the training is happening. You're training it when you're taking 20,000 different time steps, not episodes, but time step. What is the difference between a step and an episode? There is something called as a step. There is something called as an episode. Any idea?
An episode is maybe like until the termination is one episode, and then there can be multiple time steps in an episode.
Yes, yes, yes. So here you're tracking the time steps. Okay. So if I have 20,000 time steps, my one episode consists of 500 time steps. So my total number of episodes will be 20,000 divided by 500, which is roughly 440, right? 40 episodes. So I'm training it for 40 different episodes. So all I'm doing is doing model.learn. Then you save the model. You save it as sac_pendulum. Okay, this is the entire training. In 12 lines of code, you have trained your RL model. Okay, this is as simple as that. And now you want to test it, right? So you load the trained model, you do sac.load, whatever the file you had saved it as. Start a new episode. So what you do is, observation is env.reset. And earlier, when action was your action space.sample, you are sampling a random action. Instead, you do model.predict what the observation is, and deterministic is true. Okay, so your prediction is based on the observation that you have. What do you think could be this deterministic is true? Any idea?
There can be no ambiguity in the results.
Yes, yes. So if I reach the same observation at a later stage, and if I want to predict, I should get the same action back. Okay, if I have deterministic is false, that means it will give me a stochastic action. Because why? Eventually, what this model is outputting me is a probability over all the action spaces, right? And then when I say deterministic is true, that means I'm always choosing the action which has the highest probability. When deterministic is false, there might be slight exploration that can happen, right? So when think of it as an epsilon greedy. So when deterministic is true, my epsilon is set to 0. Okay. Normally you don't want to explore, right? When you're testing something. In training, you want to explore, but in testing, you don't care about exploration, right? Yeah, so this is the only plugin that you need to do. Once you trained your RL model, you loaded it. The only change that you do in the previous code we saw, where we simulated the episode, is this particular line, and then you're done. Okay, so in around 19 lines of code, you have written your own RL algorithm. Not even 19, like around 12 lines of code, you wrote your entire RL algorithm, right? Of course, I'm assuming you know what is soft actor critic, what are the different RL algorithms. But even if you don't, you can always try each of them separately and understand which works better and which doesn't work better. So let's say you can do import DQN, import PPO. You can create another copy of the environment. You can train using, let's say DQN, and say DQN pendulum. You can save it, and you can actually compare the performances. That is also possible. Okay. So now we have training framework called RLZoo. So RLZoo is basically a way to, it's basically a collection of different RL algorithms that is used to benchmark your RL algorithm that you have trained, right? So this includes training, loading, plotting, hyperparameter optimization. Everything is taken care of. You have something called as WNB integration. WNB is basically an API for logging the reward function that you have. And then you have 100 plus trained models plus tuned hyperparameters. So here you already have pre-trained models. So if you want to, like you have in the environment, in the OpenAI gym, you have multiple different environments, right? So in RLZoo, you have already pre-trained models. So you can directly, you don't have to necessarily train it again. You can just pull out trained model and you can start testing your environment on these models, right? And soon you will have a Hugging Space integration, C++ export, these will be there. But yeah, it's like a framework to benchmark your experiment. So if you don't want to train on something that people have previously done, so all trained models are saved in this RL zoo setup, right? So longer, you have tips and tricks for stable baseline 3. Maybe you should try to go through this website to understand what it is about. Yeah, again, a recap, you have the environment. The environment is designed using OpenAI Gym. We define what the action space is, observation space is, reward function is, the termination condition is, okay. In stable baseline 3, you decide what the algorithm is. Hyperparameter tuning, we don't do that. We expect stable baseline 3 to do that for us. And that's what it does also. So even if somebody is not aware of what each different algorithm does, or to avoid starting to code everything from scratch, this provides a very neat way to implement everything at a go. Okay. So yeah, that's it. You some backup slides as to what algorithm to choose. So if your action space is continuous, there are a set of algorithms that is useful for a continuous action space, like these 4 algorithms. If you have a discrete action, then these 3 algorithms. And then what do you want to do? Do you want to go for speed, or do you want to go for sample efficiency? Oh, any idea what do we mean by sample efficient? This is something we saw yesterday. When we say we want to be sample efficient, what do we mean by that?
So for yesterday's example, the slot machine example, it would be which lever is the best to be. Yeah.
No, the number of trials that I take. So if I take 30,000 trials to decide which is the best lever, then I'm not being very sample efficient. But if I do that in, let's say, 50 trials, I'm being very sample efficient. Okay. Number of trials of number of exploration trials, if it is as less as possible, then we mean to say we are being more sample efficient. Okay. And yeah,
Then
you have
Manav, then
yeah.
what is the difference between the increasing speed and increasing sample efficiency?
Speed is the training speed, right? So if you think of it like this, if you are trying to exploit a particular action, no, if you're exploring, then your speed is much higher, right?
Okay.
No, these are not mutually exclusive actually. So you can have sample efficiency and you can have speed. So speed is when you want to converge faster.
Okay. Understood. Convergence rate is faster then.
Yes.
But if it is sample efficient, then it will learn in less number of epochs, right? Because it will not need to.
It depends on the algorithm actually, like how the algorithm is actually doing the optimization. So certain algorithms require more number of samples in order to optimize. So if you have less number of samples, then your reward curve will be very noisy. You don't want that.
Okay.
If you're so when you have more number of samples, your reward curve will be much smoother. Okay. So these kind of algorithms don't, like, for example, PPO is not very sample efficient. So it requires lot number of trials, but it is fast, but it requires lot of sampling to be done to learn. But these algorithms require less samples and give similar performance. So it depends on the choice that you have.
Okay.
Okay, and yeah, you have continuous action space. Sorry, again, if you have a continuous action space, you want to normalize it. So unnormalized action spaces only work with algorithms that don't directly rely on a Gaussian distribution to define the policy. Okay, so if you are using a Gaussian distribution, always normalize the action space. So here is an example of a continuous action space, right? So if limit is too big, sample actions will only have values around 0, far away from the limits of the space. Yeah, I'm just reading through it. Just go with me. So what you're doing is, let's say your action space is from -1000 to +1000, and it's a continuous action. Okay, so if your limits are too big, the sampled actions will only have values around 0, far away from the limits of the space. Correct? Because let's say you're thinking of a Gaussian distribution. If it is between -1000 to +1000, most of the actions will be around 0 because that is the mean of the distribution, right? And if the limits is too small, the sample action will almost always saturate, that is be greater than the limits. Best practice is action space is normalized, and symmetric, and as an interval range of 2, which is usually the same magnitude as the initial standard deviation of the Gaussian used to sample the actions. Okay, so the best practice is you keep the action space between -1 to +1, as in normalize all the actions to lie between -1 to +1 if you have a continuous action space. Okay, in discrete action space, of course, you don't have to normalize because you already have discrete integer actions that you have to choose from. But if you have a continuous action space, you should always try to normalize it between -1 to 1 or -2 to 2. Anything which has a best practices to always consider an interval having a range of 2. Okay, and this is what we mean by continuous action space. So if you have a Gaussian distribution between -1000 to 1000, the slope of the hill would be very, very large. Okay, so most of the time you would be saturated between the 0th space, and if it is too small, then you don't have a lot of scope, right? So you want to the best way is to be in the limits of what the normal distribution is. So a normal distribution is basically a 0 mean and sigma 1 kind of a distribution. So the best practice would be to try to stay as close as possible to a normal distribution. Okay. So yeah, this brings me to the end of this slide. It's 10:33. If you have any questions you have. So okay, there is one session called hands-on SP3. But I want you guys to go through this, okay? Instead of me running through the code, I want you guys to open this link. It's a Google Colab notebook. You try to execute each line yourself and see how things work, okay? So once you do that, so you have a lot of exercises and you have a lot of to-do kind of a thing also, okay? So you can actually type in your own code so that you understand what is happening, okay? So and multiple tutorials as to how this can be done. So I think this is a good stopping point. You have a bunch of take-home assignments that you can do. So maybe what I can do is I should share this link. Can I share this link with you guys? I want you guys to do this collab.
If you want, you can share the link in the Q&A section by reading first.
Okay, I'll do that.
Yeah.
Okay. So go through this link, okay, and try to run this example that we discussed today. So we discussed what it is. Try to go through it. Try to see how it works, and we can continue tomorrow where we'll learn how to make our own gym environment, okay, for a very custom problem. So we'll define what the problem is. We'll make our environment and we'll try to see how the training can be done using stable baselines 3. Okay. Sounds good, right? Any other questions?
I have a few questions.
Yes.
So one thing is like, suppose if your like environment doesn't have a terminating condition, it's like you have to continuously always optimize. Then how do you like define it, and like, is it like, can you use
break
the
it off
algorithm?
at a certain? No, in practice, you always should have a terminating condition, because even if you get successful, okay, if you don't terminate, how will you do the back propagation? Okay.
Yeah.
So it's like you terminate it after a large number of time. So your capital T, your time horizon for the episode, should be sufficiently large so that you get the required behavior. Okay, so let's say it's an example of the Flappy Bird example. Okay, so that is a game where you don't have a termination condition as such. But let's say if the Flappy Bird experiment runs for 1,000 seconds, we can say with a safe assumption that this is a success case. It is doing what it is expected to do, right?
Okay, yeah.
So it's like saying, because each small uh, episode horizon is a Markovian game in itself, right? So you don't really care how you got there. So even if you start from any particular state and go for 100 or 1,000 time steps ahead in time and stop there, you can very well define a start space from that position and then go 100 time steps further. So that's what we have for the Markov property, right? So the way you got there is irrelevant to you. You only deal with what you have in front of you.
Okay.
Okay, you can always break up a bigger game into small fixed horizon episode length, and that's what people do usually. But yes, it is important to stop the episode at certain point, because if you don't stop the episode, only after the termination condition is hit, you are actually doing the back propagation in the model. If not, you're only concerned about the forward propagation. So if you have an infinite episode of infinite length, the moment you hit the success condition, you keep on doing the forward pass and never really learn what you wanted the model to learn.
Yeah. Also,
Okay.
I would like to know one more thing. Can you like suggest some tips or like some ways to like get over the like problem where, like, I think I mentioned yesterday as well, like if your state space is very large and say suppose like extremely large, and
Okay.
by pure random chance to get into a goal state, it is very difficult. Like imagine, say you're playing a very complex game, say you're playing a Mario game, and the end of the game is, imagine, like instead of the individual levels, it's at the where you rescue the princess, or like at the very end of the stage, and imagine like it's a continuous game. Imagine for a second like that. So like like if the state space is very large and the like reward is defined at the very end, so how do you ensure that the rewards are like found? Because like if the rewards are never found, then the state values will never get updated.
Yes. So it's like a
So
sparse reward condition, right? So you have to
yeah,
perform a sequence of actions to reach the goal state, and only then you get a reward. So
yeah,
that's why we need this reward shaping, right? You need to add some intermediate reward components. You
okay,
have a reward one component. So if you do something at a at a secondary level, so that should be rewarded appropriately. So that is where the shaping aspect comes in. So you will have to define multiple small reward components that drives you to the main primary reward.
I actually thought about that, but then think about of this example. Say suppose there's a golf this thing, golf playing example, and where you are playing golf and you have a hole, and the goal is given, like reward is given when you put the ball in the hole. Okay, and since the golf, that the entire ground is very large, and your actions are also like lot. There is like lot of angles you can take. There's height and elevation and force and all sorts of stuff. To just shape the rewards you defined, like if the like ball enters within a 1 meter radius inside the hole, that then you'll give it some kind of reward lesser than the goal state reward, but like to ensure that it is at least reaching that place, correct?
You can always make it a continuous reward, right? So what you can do is you can always take the distance of the ball to the distance of the hole, and that is the reward. You take the negative of the distance.
Okay, yeah.
Got it. If the distance is very large, you give it a minus value. So if you are 100 meters away from the goal, you give it a penalty of minus 100. So it's a continuous setup. So the closer you move to the goal, the reward becomes smaller and smaller, and the highest reward it can get is 0. That can be done, right?
Okay, yeah, that is actually very useful, because
Yes.
like
So it's a way, yeah, how you define. Because if you simply do a +1 -1, that if it goes into a hole, you give it a reward of 1, then it's upon chance that if you reach that particular state, only then you get some reward.
yeah, exactly. And not only that, if you like even you if you try to like just cheat a bit and say like if you are defining a 1 meter radius and it's getting a reward if it is entering that, then actually it had come in my one of the MCQs where I was solving a question. So what happens is like if you do define it like that, then when you hit the golf ball, the agent is since the it is always giving you a reward when it's inside the 1 meter, it will never put it inside the hole. It will always continuously for infinity. It will put it
Yes.
inside the 1 meter only. So that is also one drawback, I thought.
Yes, yes. So it's dependent on how intelligently you define what the reward should look like. Always the best practice is if you have a continuous kind of a reward, like at every step you get a reward. So when you define it as a distance to the goal, so at every position in the environment, you get certain reward, right? So always try to make sure that the reward is less sparse as possible.
Okay, yeah. But
Okay, so
then this also also this problem where like you need to ensure that the reward given at the goal stage should be significantly much larger than at any intermediate
yes,
stage,
yes,
right?
yes. That is the shaping aspect, right? You have to play around with the numbers. The primary reward, the secondary reward, that is exactly what the reward shaping is. That is only done through trial and error, or if you have a strong mathematical intuition behind it.
Yeah, I learned it the hard way. I actually tried solving a problem and I got stuck.
Yeah. Yeah. So you have to tune the rewards that way. And that is, like I said, the biggest assumption that RL makes is your agent is only as good as the reward function that you design or you define, right?
Okay. One last question. Like, can you like, do you know for any libraries for like multi-agent support, like for defining multi-agent algorithms or like for like any environments for multi-agent?
Most environments that make use of multi-agent, stable-based density doesn't have multi-agent support, but there is something called as RL-lib. You can probably take a look at it, but it's not very simple. Okay, it's slightly complicated. You have to actually go through the documentation on how this is working, and the interface is not very simple. But that is one library that supports multi-agent RL. But as far as I know, in our case, we usually do it ourselves. We code everything from scratch when we want to do a multi-agent training.
Okay, I see. Then you need to code the environment as well and the agent algorithm as well,
Yes,
everything.
yes. Environment, you anyway have to code because your task is very specific on what you want to achieve. Let's say, for
Yeah,
example, you have the traffic control. So you have to design the environment. I don't know, do they have a gym environment for that?
I don't think so.
Yeah, so then you have to design the environment yourself and then algorithm also, like let's say soft actor critic. So if I want to do a multi-agent setup, I have to actually write down the entire line by line how the optimization looks like and so on. And then that way I have more control over my code.
Okay, yeah.
Okay. So yeah, go through this, guys, and we'll meet tomorrow then. Okay. Any other questions?
Okay, I think there are no more doubts. We can end the session.
Okay.
So yeah, thank
Okay.
you to Manav once again for this wonderful session today, and we'll see you tomorrow at the same time.